Hello students and welcome to lecture 13 on orbital diagrams. Let's first review subshells and the number of orbitals that can be found in different types of subshells. For any S subshell, you'll always have one orbital and you'll have 2 electrons maximum that can fit in that one orbital. For any P subshell, you'll always have 3 orbitals and you'll have 6 electrons maximum that can fit in those 3 P orbitals. For the D subshell, you'll always have 5 orbitals, and the maximum number of electrons you can fit in those 5 orbitals in the D subshell are 10 electrons. For the F subshell, you'll always have 7 orbitals, and the maximum number of electrons you can fit in those 7 orbitals is 14 electrons. All right, so make sure you wrote those down. Next, let's discuss energy. Generally, orbitals in the same subshell tend to be degenerate. By degenerate, which you should write in parentheses, they tend to have the same energy. So you can just write down orbitals in the same subshell are first of all degenerate, and then the parentheses just write same energy. For example, if you look at the 5 3D orbitals, or the 5 orbitals in the 3D subshell, they all have the same energy because they're all at the same level of energy. Similarly, all of the 7 4F orbitals, or all 7 orbitals in the 4F subshell have the same energy, which is why they're at the same energy level of energy in terms of amount. Okay, next let's discuss Hund's rule and Pauli exclusion principle. So Hund's rule states that electrons occupy orbitals of the same energy so that they can maximize the number of electrons with the same spin. In other words, what this means is that electrons will occupy all orbitals in the subshell with as many spins up as possible before any electrons are paired with opposite spins going down. So for example, let me show you an example down here that I want you to write at the side of the definition because I did leave some space in the homework. Let's say with the 2p orbital, and let's assume they all have equal energy, meaning that all of the 2p's orbitals are degenerate. If we have something like 2p3, what we're going to do is we're always going to try to fill everything up singly before we even pare it down. So for 2p3, we would go up, up, up before we do anything, because you want to have as many orbitals of the same energy as possible with the same spin going up. All right, so whenever you have anything from 1 to 3 for 2p, for example, you would always want to put everything up as much as possible. The only case in which anything would pare down would be after we filled everything up halfway with the up spin. So if it's 2p4, we filled all 3 of the orbitals in 2p up with the up spin, and the 4th one would be sort of like a last-ditch effort, and that's where we would put the spin going down. If it were 2p5, then we would put the 5th electron pairing down like this, and for the 6th electron in 2p, we would put it going down like this. So really, as much as possible, Hund's rule just states keep as many electrons occupying orbitals of the same energy in a way where you have as many spins up as possible, okay? Because you should always do this as much as possible, just for the sake of what Hund's rule says. All right, so if you did the d orbital, for example, and if it were like 3d5, for example, then you would have to put everything spin up before you even did anything else, because you want to always fill as many orbitals of the same energy up with the same spin as possible going up. Only in the case of 3d6 would you start pairing up. Okay, so that's the idea of Hund's rule. Next up, we have the Pauli exclusion principle, which states that no 2 electrons can have the same set of 4 quantum numbers. So the idea here is an orbital only holds a maximum 2 electrons each with an opposite spin. The reason why this is important is let's take the example of 2s, the only orbital in the 2s subshell, which we can also call the 2s orbital, since there's only one orbital in the 2s subshell anyway. Let's say we have 2 electrons both in the only 2s orbital. In that case, what you know would be true is they would both be in the 2nd electron shell, since n equals 2 in the front. You'd know that since you have an s in the back, that l equals 0. You also know that the only possible value for l equals 0 would equal ml equals 0, since there's no positive or negative 0, there's just 0. So you'd only have one possible ml value. Being that they're in the same subshell and the same orbital, both electrons would have all 3 of these same values. Therefore, the only value that's left is ms. In order for these electrons to obey Pauli exclusion principle, which it always should for orbital diagrams, one would need to be up and the other would need to be down, like this, if they're occupying the same orbital. Because if one's up, then that's positive half. The other's down, it's negative 1/2. So in order to occupy the same orbital, which means you have the same n, l, and ml values, then the ms values must obviously be different, because they can't both be up, because then all 4 numbers would be the same, and that would violate this. Therefore, to not violate it, you have to keep one down while the other goes up, so that their ms values are different, and so that they don't have the same 4 set of quantum numbers. Okay? So up down is good for any single orbital. Up is bad because that would make all four values the same, which you don't want. All right, so this is already done for you in your packet, so you don't really need to write this down. Just make sure you understand this and study it. And for number 2, it says explain why 2 electrons in the 2s subshell must have opposite spins. Let's remember, just as we saw here, no 2 electrons in the same atom have the same 4 identical quantum numbers according to the Pauli exclusion principle. If both electrons are in the 2s subshell, specifically the 2s orbital, since there's only one orbital in 2s, then they have the same n, l, and ml values. So obviously, they must have opposite spins so that not all 4 quantum numbers are the same, because if one's up and one's down, that means that allows their ms values to be different. The up being positive 1/2, the down being negative 1/2. All right, next let's go over orbital diagrams. Now this represents sort of a different way to show electron configurations, but in terms of electron spins and how they fill things up in order. Step 1, you have to write the electron configuration. Step 2, you have to draw lines for each subshell's orbitals in the configuration. So for any s subshell like 1s, 2s, 3s, 4s, 5s, 6s, or 7s, you always have to have only one orbital for that subshell. For any p subshells, you should show 3 orbitals like this, or like this, or like this. This is what they look like. For any d subshells, you should always have 5 orbitals, something like this, or this, or this, or this. For the f orbitals, you should always have 7. Sorry, for the f subshell, my bad. You should always have 7 orbitals that look something like this or like this, okay? Then what you have to do is, after you draw the correct number of orbitals for each of the subshells in the electron configuration, then left to right, you have to put a spin up in each orbital as necessary until all orbitals are half filled. Then step 4, left to right, you have to put the spin down electrons in orbitals of the same subshell only if you need to. If you don't need to, then just stop where you need to. Step 5, you have to move on when all the orbitals in the subshell are filled, making sure you repeat steps 2 through 4 till done. So for example, if you had something like, presuming everything else has orbitals filled up with a spin up and spin down for each orbital, let's say we have 3d5, what we need to do is, before we do anything, we need to make sure that these 5 electrons always have a spin up electron first, because that's what you always must do, fill up or half fill all the orbitals as much as possible with spin ups. Since this matches 5, that would work. Now on the other hand, let's take another example, and let's say it's 3d7. What you need to do is, just like before, for the first 5 electrons in that 3d subshell, you need to go 1, 2, 3, 4, 5, and then the 6th and 7th one, since you've half filled everything, now you can go on to step 4 and start pairing the spin downs like this, 6th and 7th like that to get 3d7. So that's what I mean by an example. All right. So I also want you to note, sometimes a noble gas configuration is used to condense or shorten the orbital diagram, which I'll show you in a minute. All right, but let's try some orbital diagrams for the following and circle the valence electrons in each. Let's remember the valence electrons are always circled for the highest principal energy levels only. So for example, with S, if you look at the configuration, you'll see that it's 1s2, 2s2, 2p6, 3s2, and 3p4. So what we have to do is, for the 1s2, we paired up singly first going up, and since there's a second electron and there's no other orbitals left for 1s, the only other logical place we can put it is in this one orbital. Since one electron's up, the other must be down, so we don't violate the whole idea of the Pauli exclusion principle. Okay, for 2s, you know, both of them are filled, so one goes up, and since there's nothing left, the other one also goes in this orbital. So in order to not violate Pauli, we have to put it down. For 2p6, obviously, you know, the first 3 have to go up, and since all the orbitals are half filled, you know that 4, 5, and 6 can go in no other orbitals. So you have to put the other 3 going down so that you don't violate Pauli exclusion principle. All right, for 3s2, you know that 1 goes up, and since there's actually 2 electrons, there's no other place to put the other one, so you just put it in the same orbital, but with the spin down, so it doesn't violate Pauli. For 3p4, on the other hand, you have 4 electrons in the 3p subshell. So what we need to do is first put the spins up singly for the first 3 electrons in 3p, and for the 4th electron, since everything else, all the orbitals in this 3p subshell are half filled, now you can start putting the spins down because there's no other option left. So for the 4th one, you just pair it up with the first orbital of 3p with it going down, so that you have 4 electrons in 3p. So each of these spins represents 1 electron in a sense. All right. For Mg, we know that the electron configuration is 1s2, 2s2, 2p6, 3s2. So all you have to do is, since all of these are filled, a shortcut to do this is just fill up all the orbitals, since if you pass them, you presume that the orbitals are filled up with the spin up and spin down anyway. So when you do that, it shortens your time, and it just leaves you with this. And the only thing you have left that may or may not be filled is the 3s subshell. If you look, Mg's configuration is 1s2, 2s2, 2p6, 3s2. So for the 3s subshell, you have to be careful because the first electron must be paired spin up, but you notice it's 3s2, so the second electron needs to also go in that orbital. How? Since this is spin up, and we know we can't violate Pauli's exclusion principle, we have to pair the other spin going down like this to get 3s2. So this is what Mg's orbital diagram looks like. All right, and the number of valence electrons obviously is based on the highest principal quantum number. For S, it's the highest principal quantum number is 3, so just circle every subshell with highest principal quantum number 3, and you circle 3s and 3p. And if you count the number of valence electrons in this, where the valence shell is, you see that you have 6 valence electrons. For Mg, the highest principal quantum number is 3, so you only circle the subshell with 3, which is 3s. And if you count the number of valence electrons in here, you see that there are 2 valence electrons. Okay? Next, let's discuss some more orbital diagrams. For K, we know that the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So we can just presume that all the other orbitals that come before the one orbital in the 4s subshell are filled with the spin up and spin down, because if you pass them, you presume you fill them up. Right, so let's fill up all these orbital boxes. And then for 4s1, we know that there's only one electron, so logically you can only put the spin up because the first electron in any orbital is always going to be paired to spin up singly before you move on. So we can stop here, and now we have the complete configuration. And obviously the valence electron is in the highest shell, which is 4, or the highest principal quantum number, and the only subshell with the highest shell number of 4 is 4s1. And if we count in here, there's only one valence electron in K, which matches up to what you have learned. So for ZR, I want you to take a minute and just figure out what you need to fill up by looking at which subshell ZR is in. So if you look specifically, if you check, ZR is in the 4D subshell because it's in the D designation, and it's in the 5th period. So you do 5 minus 1 for the principal quantum number, which is 4, and it's in the D block, so it's 4D. Specifically, how many into the 4D block is it? If you start counting at Y, you get 1, 2, so you know it's 4D2. So what we need to do is fill up everything before 4D2 with 2 electrons in each orbital, and if you do that, you get something that looks like this, since all these coming before the 4D2 are filled. And obviously, since you have 4D2, you have to put the electrons with the spin up before you pair anything. So if you fill up the first 2 boxes, you get 4D2 like this, and nothing pairs up. So you've actually filled in 2 electrons in the 4D subshell, so you're done. This is the orbital diagram for ZR. And if you circle the valence electrons, which are only in the highest principal energy level, you'll see that the highest principal energy level out of all of these is 5, so you only circle the 5s subshell. If you count the number of valence electrons in here, you'll see that you have 2 valence electrons for ZR, which checks out with what you know. For SE, you know that if you check it, the configuration is, I believe, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. So what you need to do here is just fill up everything before 4p. Obviously, since you're passing, you presume you fill it up with 2 electrons in each orbital for all of the subshells. So if you do that, you get something that looks like this. Now for the 4p4 part, all you have to do is take the first 3 electrons in the 4p subshell and put it spin up like this. And then for the fourth electron in the 4p subshell, since everything else is already put spin up and all the orbitals are half-filled in 4p, now the 4th electron must go in one of the half-filled ones, since there's nowhere else left to put it. So we put the 4th one spin down like this, pairing up with the first spin-up electron, and we get 4p4. And obviously the valence electrons are only circled in the highest subshell, which is the 4th subshell, so we circle the ones with the highest principal quantum number 4, which are 4s and 4p, and if you count the valence electrons here, and here you see that you have 6 valence electrons, which checks out with what you know. For CO, if you check the subshell it's in and how many you go in, you count into the 3D subshell. Since it's in the 4th period, so the principal quantum numbers 4 minus 1 are 3, and it's in the D block, so it's in the 3D block. How many is CO in? If you count, it's 1, 2, 3, 4, 5, 6, 7. So you have 3D7 in here. Alright, so what you need to do is everything before 3D7 is filled up, and if you do that, all of the subshells filled up before 3D look like this. And then for 3D7, you have to put the first 5 electrons with the spin up in the 5 orbitals in 3D, since you have to fill it up halfway until all orbitals are half filled. Then for 6 and 7, since we have no other orbitals to put it in, now we got to put the 6 and 7 ones paired spin down like this, and you get 3D7 like this, okay? Now to find the valence electrons, in CO all you have to do is circle the electrons in the highest principal energy level. The highest principal energy level out of all these is 4, so you just circle only the subshells with principal energy level or principal quantum number 4, which is just the 4s subshell. And if you count the number of electrons in here, which are the valence electrons, you see that CO only has 2, which matches up with what you know. Last, let's discuss exceptions to electron configurations. Sometimes expected electron configurations deviate from what's actually seen. This is because half-filled and filled subshells are considered more stable as they lead to lower energy overall. So atoms will tend to rearrange their electrons to attain these more stable configurations. For example, in CR, the expected noble gas configuration is Ar4s2 3d4, where 4s is filled, but 3d4 is not half-filled, nor is it filled. To make this more stable, one 4s subshell electron promotes to the 3d subshell, leading to CR's more stable actual configuration of Ar4s1 3d5. And this configuration that's actual is more stable because having a half-filled 4s and a half-filled 3d subshell is more stable than just having 4s fully filled. All right, a similar case occurs for MO. Now for Cu, the expected noble gas configuration is Ar4s2 3d9, where 4s is filled, but 3d9 is not filled nor is it half-filled. So to make this configuration more stable, one 4s subshell electron promotes to the 3d subshell, leading to Cu's more stable actual configuration of Ar4s1 3d10. And this is more stable because it has a half-filled 4s and a filled 3d subshell. And this actual configuration put together like this is more stable than just 4s being filled by itself, okay? Finally, please complete these practice questions for tomorrow. See you tomorrow. Bye-bye.